All right, welcome back. So for the afternoon session, our first speaker is Jonah. So he will tell us about large fluctuations in the Larsen limit.
Thank you. Can you hear me? Is this on? This is on? Okay. All right. Yeah, thank you very much for the opportunity to speak. I'm going to talk about mostly work in progress, but then motivated by this paper I wrote last year with Ed Witten, and there's some related papers on similar things by Elliot and Hong, who will be here. So, talk to them too. And as it's a work in progress, my thoughts on the subject aren't actually fully formed. So I'll be very happy to hear any thoughts. So ADS CFT has been extremely successful for understanding quantum gravity in open universes, namely asymptotically ADS, or open spacetimes. But it would be really nice if we could use some of the same technology to understand quantum gravity in closed universes. There's a possibility we live in a closed universe, and that would be nice. So it'd be nice to understand closed spacetimes with the same technology, so from a CFT. Okay, so there's an obstruction to this. Which is that closed universes and this was the subject of the paper and the related papers in ADS CFT, do not have large n limits. So they don't have semi-classical limits. And I'll explain what I mean by that. Okay, so a bit more formally, what I mean by this obstruction is that if we are given some set of states, some sequence of states, one for every value of n, so I'll call them psi n, and these are supposed to describe a closed universe. So we're given the sequence of states. There's been some interesting proposals. For example, there's been states that from the path integral appear to be dual to some asymptotically ADS region that's entangled with some Big Bang, Big Crunch cosmology. So there's some entanglement, and then the space-time has two disconnected components in some of these examples, where you have a closed universe. And so it'd be nice to understand quantum gravity in these Big Bang, Big Crunch space-times. But the argument was that we showed that if you have some sequence of states that's supposed to describe these kinds of space-times that have a closed universe, then for all operators in your boundary theory, so for example, take some simple single trace operator. If you take the limit as n goes to infinity, so these single trace operators can be defined at any n, and we take the limit of the expectation value as n goes to infinity, this does not exist. And from my perspective, without a semi-classical limit, it's hard to define what we mean by having a closed universe. So this kind of, so in order to say that we're describing quantum gravity in a closed universe, we want to have some semi-classical spacetime. Yeah.
Hey, this might be exactly the point you're making, but it feels a little bit like the argument is circular. Like the statement that psi n describes a closed universe kind of assumes there is a good large n limit.
Yeah,
so that like just saying that you believe there should be a closed universe as the large n, you know, the CFT states at every n don't have an obvious Einstein gravity interpretation, right? So why do we think that they should describe a closed universe, especially given you just showed that they don't, you know, observables in the large n limit don't exist around these? This might be your point, but I'm asking if it's circular, if the very first line of that board is almost like, yeah.
Well, suppose.
Oh, okay. Okay. Yeah. Okay.
So
then. Yeah.
So we want to assume we have this,
Yeah.
and there's well-motivated reasons to think that there are these kinds of spacetimes. For example, people have constructed similar-looking states.
Yeah, with these
from the
shells.
gravitational path integral.
Yeah.
And the point is, you know, assume that, and then kind of a proof by contradiction that wasn't consistent.
Okay.
As
Yeah.
a semi-classical limit.
Okay. Yeah. So it's not circular. It is kind of your point. Yeah.
Yeah, and there are states like this in the gravitational path integral from a bulk perspective. And one of my goals is to still try to understand these spacetimes and not totally give up hope.
Yeah.
And one of the main questions in the field right now is what is the gravitational path integral telling us if it's giving states like this in the bulk, but there's no CFT large n limit.
Yeah.
So maybe there's something to save, maybe there isn't. This statement is just that there isn't in the usual ADS CFT dictionary.
Yeah. Okay. Thank you.
So could you explain why this limit does not exist?
Yeah, that's what I'll do next. Well, I'll do it too quickly because I want to get to some other things, but I'll tell you the basic mechanism, and I'm happy to talk more about this later. Okay, so the mechanism is we use so we're doing, this is a CFT statement, it's CFT operators and CFT states. But so we use the gravitational path integral and the ADS CFT dictionary, so this is some partition function in the CFT equal to some gravity partition function. And then we set up these correlation functions as some asymptotic boundary conditions, and then ask what the gravitational path integral is giving us. And so the result of looking at the gravitational path integral for these classes of expectation values leads to that there's a variance in these expectation values there's some finite variance in these expectation values as we go in n. So if you have some list of numbers, just the expectation value at each value of n, this won't ever settle down. There's some finite variance as you go along the line. And this finite variance means that the sequence isn't converging to a fixed number. And what's leading to this variance is wormhole configurations in the gravity path integral. I can make 2 copies of this. We're computing a variance, so we're looking at statistics. And there's contributions to the path integral that have wormholes between the closed universes. And I can describe the math, and other people have also looked at very similar things with closed universes and how you get finite variance. But our point is that certain wormhole configurations to the gravitational path integral lead to these expectation values not having a large n limit. So that was the basic mechanism there. One of the things that we have trouble pushing in this direction further is that these states are not particularly explicit. So it's sometimes hard to do boundary calculations when we don't have a very explicit sequence of states that what we mean. And
are you saying you're missing some states? If you include them, you'd be able to.
So there have been proposals for what these kinds of states with closed universes are, but they're not quite explicit enough to like do just pure CFT calculations and look at this limit very carefully. So we needed to go to the gravity path integral and calculate this variance.
Then you computed the contribution, wormhole contributions as well.
The what?
You compute the wormhole contributions.
Yes. Yeah.
And you showed that those are necessary.
Yeah. If you use standard like wormhole stuff in the gravitational path integral, you'll find that no matter what, as long as the entanglement between the ADS region and the closed universe is finite, which is the standard case, then this limit can't exist in this finite variance. So it's just a pretty general argument. But on that point, it's important that that this does not happen for a fully evaporated black hole. So one reason we're sometimes interested in closed universes is that a fully evaporated black hole, let's say an ADS, the Cauchy surface roughly looks like, well, I'm being schematic, but you have some interior region and then the fully evaporated black hole in ADS with all of the Hawking radiation. And the interior of the black hole is morally a closed universe. These arguments don't mean that the state of the Hawking radiation at late times doesn't have a large n limit, and the loophole was just that the semi-classical entanglement between the Hawking radiation and the interior diverges in the large n limit. And the argument also doesn't hold for any other spacetime that doesn't have, usually in ADS CFT, we are considering small excitations about some background spacetime, so some coherent state. And so in those cases, wormhole contributions aren't going to spoil the large n limit. So it seems particularly special to having a closed universe.
Yeah, when you say large n limits, you really mean large n limits of finitely many products of single trace operators, or?
Yeah, so I'm fixing my operator and then fixing my operator and taking sequences of states. So this operator isn't growing with n.
Yeah, so we're not allowing even polynomial complexity in the operators or anything.
Yeah, I'm not letting the operator change as I change n. It's another interesting question of what happens when you consider operators that are, say, growing with n, more complicated operators where you might be able to access something more complex. That, I don't have anything precise to say, but well, yeah. So this statement that you have finite variance in the large n limit, which obstructs some semi-classical physics, is what I mean by the title, that you have large fluctuations in the large n limit. Okay, so we want to understand what is the gravitational path integral giving us if it's not these states. So as I mentioned, people have constructed interesting states using the gravitational path integral that looks like a path integral on the boundary. It looks like you can describe closed universes, but there's some obstruction. So what is the gravitational path integral actually giving us? What is the gravitational path integral? And to explore this problem a bit, I'm going to go to so let's go to a simpler setting. Simpler because I can be a bit more explicit. I had mentioned that I have a bit of trouble being explicit with these states, and I had to go to gravity, but I would like to have a clearer boundary definition of these problems. And something that's been studied quite a bit in the literature, where you have a very similar issue with large fluctuations, is the spectral form factor. In particular, the microcanonical spectral form factor, which is defined like this. People call it y delta of t, and it's equal to the absolute value squared e to the minus IHT, and then you have some window function, some microcanonical window function. You could take to be some Gaussian with some width delta, where the width is very small, but it's it's not too small. So this is the spectral form factor, or the microcanonical version of the spectral form factor, and it has this famous behavior in general chaotic quantum systems. So y of delta and t, and I'll do this on log-log scaling because you have to go to very late times to see some of the interesting physics. And so at first it goes down, and this is the disconnected piece. This is, well, not disconnected. I'm writing this in a fixed Hamiltonian, for a fixed Hamiltonian. So this is just a single function. So first it goes down in a very smooth way. And then at some point, that we'll call t dip, it stops decaying, and it starts to grow, but oscillates wildly. And then there's a time when we hit the plateau, and the plateau is times of order exponential in entropy. And I'll comment on what the t-dip time is. But the important part that's showing spectral repulsion, the chaotic part of these theories, is this linear ramp. So on average, for example, if you time averaged, this is some linear in time ramp. And then at these very late times, you just get the plateau from the discreteness of the spectrum. And that plateau would even happen in a non-chaotic theory. So this ramp regime is really the random matrix theory universality piece that happens in this quantity when H is some chaotic Hamiltonian. So importantly, in this regime, the signal, the fluctuations, the variance is just as large as the signal. These are very large fluctuations. And that's not true over here. Here it's just some smooth behavior. And so in this regime, if you take, say, the Hamiltonian for your favorite holographic theory, and evaluate it during the ramp regime, the fluctuations are not going to lead to some good limits. It'll keep oscillating as n gets larger and larger. Nevertheless, there's a very important gravity explanation of this linear in T growth. So Saad, Schenker, Stanford found the double cone wormhole, which I'll write now. So if I have the ADS black hole eternal black hole, and I take some t intervals on the boundary and periodically identify here and here, and there's some I epsilon prescription I won't really talk about much, but is important at this surface. There's a solution, a gravity solution, so it looks like this double cone, and it's Lorentzian. And the gravity path integral for this double cone reproduces this linear in T behavior, and it's a very universal saddle and seems to be characterizing the chaotic nature of holographic conformal field theories. Yes?
Make sure that there is this delta over which you are, like some window.
Yeah, so one thing that was important for them is that they had to go to the microcanonical ensemble for the black hole, so studying the boundary conditions so that it's a microcanonical ensemble, in order for there to be a saddle. So I think originally in the black hole literature, people looked at the canonical version of the spectral form factor, which I would just have some betas, and that one doesn't have a saddle. And so they actually went to the microcanonical saddle. And the microcanonical is actually going to be a sharper test for us, because in the canonical ensemble, if this was some Gibbs weighting, the T dip time would be some exponentially late time. It'd be something far, far in the future. But you can take some Gaussian weighting, some order 1 Gaussian weighting, and have that this dominates over the disconnected piece, so some just whatever the microcanonical partition function is without allowing the wormhole contributions. This can dominate over the disconnected piece. So this is what we call T-dip at times that are order square root in the entropy. So it's just some very short time comparatively to these exponentially late times. It's still a long time. This is still scaling with n, but it's relatively short. So in this case, this seems to be telling us something very important physically about the boundary theory, the random matrix theory behavior. So we don't just discard it just because it doesn't have a large n limit. And I mean, maybe we should, but that's not what I want to say. And I don't think most people would want to discard it because it seems to be giving us really important physics. But it's not giving us the physics of some single CFT, because the single CFT will be some erratic behavior. And so this is the analog of these closed universe saddles, where there's some important physics there, probably, but it doesn't correspond to just the large n limit of, say, n equals 4. And so this is the factor, or one instantiation of the factorization puzzle. And in particular, I want to ask, what does the double cone mean given the fact that t, the time that we've chosen, can be fixed on the boundary precisely. So sometimes the explanation of this smooth T behavior, people say, is like a time average. If you do some time averaging in these fluctuations, you would just get some linear ramp, some order, something that's smooth. But ADS-CFT is not telling us to do this. We don't have to average over time, we can really just fix time precisely in the non-gravitational theory. So to me, it's not satisfying to say that the ramp is giving us an average over time, because we've really fixed the time when we've looked for this saddle. So what does it mean, given that we can actually just fix the time to some specific number? And generally, there's no ensemble of H's in higher dimensional cases of ADS-CFT. So this saddle is present in all dimensions, but low dimensional cases like JT gravity have some ensemble description, and so there's no problem explaining the smooth behavior in those cases, because they're dual to some random matrix ensemble, where when you average over the ensemble, you smooth out these fluctuations. So in those cases, and perhaps 3D gravity might have some ensemble description, there's not really a sharp problem. But in higher dimensional cases, for example, n equals 4, we don't really have anything to average over, and yet this seems to dominate the path integral and give us some important physics. So this is a puzzle, and I'm going to talk about a speculative way to approach it that doesn't involve averaging over t or some other parameter that n equals 4 doesn't give us. And so the idea is that the subtlety in this matching between bulk and boundary is the G Newton goes to 0 limit. In the bulk, the semi-classical limit where this saddle really makes sense, or as we're really doing perturbative gravity about such a saddle. And on the boundary, this is the n goes to infinity limit. And we're going to ask if the double cone plus any corrections can be reproduced and by double cone I mean other things that don't seem to have large n limits but have good gravity path integral descriptions by averaging observables in n being the rank of the gauge group. So we've taken this semi-classical limit, and this might be the weak point in the identification of the gravitational path integral and something in the CFT. So at finite values of n, we think that it's some exact duality. But on the boundary, if we take the large n limit, we don't get something that exists. We don't get a limit existing, while in the bulk, it looks like a perfectly nice, smooth saddle. So we're going to focus on n, which is really the only parameter in the game here, and ask about if observables, as computed by the gravitational path integral, can be understood as some limit like this, where we have some weighting function in n and the observable at that value of n.
Is that a definition, or is it a
This has a question mark over it because I don't know if it's true. So these are fixed. These are well defined. You take the finite n theory and compute some observable. This is yet to be determined, but and this is the answer that the gravity path integral gives you.
Ensemble. Yes, maybe.
This is defined from the gravity path integral. It's giving us something like this ramp, this linear and t ramp. But how can we interpret this using just the fixed theories, where we don't really have the only ensemble we're really given here is in n. Yes.
Are you asking for this to be like a whole trend series of corrections, or just repeating like n equals infinity?
Yeah, I'm going to be. I'm not going to be terribly ambitious in that I only want to reproduce. For now, I'm focusing on the leading thing plus perturbative corrections. So if the observable has a 1 over n expansion, so a general observable from the gravity path integral, we have some background saddle, okay, here, and then you could look at perturbative gravity corrections on that, which will give you some 1 over n expansion around this saddle. I'm not asking right now on whether you can reproduce other non-perturbatively suppressed things. Yeah. Although that would be great.
Sorry. Is this proposal different than what Hong is proposing?
Hong's papers was, well, I don't think any of our...
Can I reproduce the slim sum ff of n with this filter, with his filter?
I don't think there's any specific filter that's been proposed yet.
No, yeah, morally I'm saying.
Yeah, it's the same. That was one of the papers I was referencing that says similar things. Hong has a couple recent related papers. There's a couple open questions. One, could anything like this work? And two, if it does work, then how do you actually do this averaging? These are aspirational right now.
As n increases, the contribution of those operators becomes more and more leading order.
As
increasing, those contributions become more leading order in this sum.
So like a simple thing we could do here is 1 over n. So let's think about some observable that already had a good large n limit. Then if you even just did this simple kind of averaging, you wouldn't mess anything up with the original ADS-CFT dictionary because it already had a good 1 over n expansion, and so these are going to tend to that, and it's just good, and your whole sum is going to be dominated by that tail that already converged. So in cases where these do have good limits, this doesn't change anything. The point of doing something here is if these guys did not have good limits, this can sometimes help you in changing you to have a good limit. Yeah, so these are really like tail observables. Like all that matters is what's happening at asymptotically large. It won't change if you change some finite number of ONs. Okay, so to understand if this kind of thing can help, we need to understand how these observables at different values of n are correlated. So if they're completely independent random variables and you're averaging over say n IID variables, then we get fluctuations. So we have order square root of 1 over number of samples that we've done, fluctuations. And so while something like this average. So while this limit, let me, lim sum of ONs, F, will have a good limit, even though the individual ones won't, because the averaging will average over these fluctuations. The 1 over n correction will not make sense. And this is because these statistical fluctuations are larger than our perturbative series. And so just a simple averaging over these integer values of n doesn't seem like it's going to help much. Maybe it would give us the leading term, but not the whole perturbative series, which we think is meaningful. So we have to make more assumptions or explore more things that haven't been worked out yet, but is morally related to this fortuity story that I think we'll hear a lot about.
If you define some analytic continuation for non-integer values of n, is that still?
Yeah, so good. That's my next assumption is assume the theory that we care about. For example, n equals 4 can be defined for now real values of n, not just on the integers. Some theories do have good analytic continuations as theories. So you could hope that for these theories dual to gravity, they also have some analytic continuation. This is optimistic, but I'm an optimist.
The whole theory to be analytically continued in n, or do you just need the observable to be analytically continued in n?
I want the theory to be analytically continued in n, because then there's some canonical choice. I think if you have a list of numbers and you just want some interpolating function, you're usually given too many choices and it's not clear. And in some cases, there's the natural choice, canonical choice, but usually, and for example, in these cases, there's not a canonical choice. And in this case, I want the theory to make sense and to give me what this continuation is. Just interpolation isn't going to be enough. And the reason to go here is because now we can average over, now we have many, many more variables, infinite number of variables. But the question is, how many variables are independent? So the fluctuations are going to go like 1 over square root of the number of samples that we have that are roughly independent. And so we need to understand how theories decorrelate as you change n. So this gives us a chance and I'll go to a theory soon where I know how to do the analytic continuation. So this won't all be speculative. Yeah.
Can I ask a question that's a little bit back there? Could you go the other way? Define a right-hand side where you define a set of functions f, and then from there determine what the gravitational path, what operators belong in the gravitational path such that they reproduce those particular functions.
Like it could define which things you sum over. Yeah, this feels morally like what people do in like 3D gravity with averaging. I don't know in the case with averaging over n if you could do such a thing, but for example, there's this problem with just averaging over n variables. But people have found a lot of success in these other examples where they define it some average over some ensemble of CFTs, and then they have a gravity interpretation. So that's a reasonable thing to think. But yeah, my main question is, I know what the answer is on the left-hand side. It doesn't make any sense in terms of CFT. So we have a chance, given ONs decorrelate quickly. Like we can get many independent samples between n and n plus 1. So from gravity, something you could study is this microcanonical spectral form factor, but look at correlations between the spectral form factor. I'm just going to call this microcanonical thing z at value n, and z at n plus delta n, where delta n is much less than n. And so we're asking for correlations. For now, let's just think about integer delta n. So there's a double cone contribution from gravity to this correlation function. Well, I guess, yeah, well, I'll leave that. And there's a contribution that's a double cone, but we have different n's, different values of n on the different asymptotic boundaries. And so there's a saddle with delta n D3 branes, where you cross the D3 brane and the flux jumps. So this is the same double cone, and because we've taken this to be some small number, this isn't changing the background geometry, but now you get some action. So this has been studied by, in a couple of papers several years ago, like Kudler-Jensen and Merolf and Mahayan. But you can look at this and interpret this answer for the action of these D3 branes as this connected correlator. And what you find is you still get the linear in T, but now it's suppressed by e to the minus some number, some order 1 number. That will depend on your theory. This kind of thing will work in other versions of ADS-CFT. But it will look like this. So you have the time and delta n in some number. And so we're asking, how fast do things decorrelate? And so I'm going to interpret this as defining some correlation length as you're changing delta n. And that's just going to be the inverse of this and this. So this is just 1 over this order 1 number times n times t. So we see that things decorrelate very quickly in n. And in particular, you'll get order n times t, a number of independent samples between n and n plus 1 under this assumption. So as I said before, the dip time was like square root of entropy, or it could be as early as square root of entropy, which is order n. So we put an n here, and so now we'll get, and then there's this additional n from summing all of from 1 to n. And so in total, you get n cubed now different samples. So you can slightly improve upon the number of, at the dip time, you would be able to get, so at the dip time, you can get order 1 over n to the 3/2 fluctuations. So you could, in principle, recover the first term in your perturbative expansion. But this isn't so much better, but it's a little bit better. At exponentially late times, but still well before the plateau, you'd be able to recover the whole series, because t is if t is some exponential in n, then we have some huge number of independent samples. So I want to explore whether this this interpretation of this answer with the D3 branes made sense. I've been considering, analytic continuing between n and n+1 and how fast things decorrelate. And I don't know how to define this theory at real n and how to do these computations, so I'm going to go to something simpler and try to get something, and try to see if this is something physically meaningful. Yeah.
So if you allow n contain r value, and then on the average side, you can actually do integral instead of sum. And in that case, I think the fluctuation can be much smaller, because integral means you solve infinite many terms.
Sorry, if you do what?
So there you try to average over n,
Yeah.
but if you allow n to be r value, and then you can average by using integral instead of using sum.
Yes.
And in that case, I think the fluctuation can be much smaller.
Yeah, you can get a smaller fluctuation because you're averaging over many things. But you still need, but if it's if we have some real valued function, if we have a function of the reals, we care about how fast it's fluctuating in the reals so that you get independent samples. So it only helps get rid of, noise if you're averaging over independent samples. So it's not like we immediately go to zero fluctuations just because we're averaging over an infinite number of things.
Oh, I see.
We're still averaging over a finite number of effectively independent things.
I see. So that 1 over n to a 3 half, that is for the integral case, is that?
Yeah, that would be for the integral case using this calculation, because t is order n multiplied by n, and then we also had the original sum, so that's n to the third. And so we have n cubed samples, and we take the square root for the fluctuations.
Thank you.
Yeah. But the fluctuations are dying off in time, because if t is going bigger and bigger. Okay, so I want to understand whether this interpretation makes sense. And so I'm going to go to a calculable model where we can actually interpolate between different n's to see if this analysis was reasonable. And so let's consider a large random matrix. That's L by L. We'll take some invariant ensemble, some single matrix. And I'm going to think about a subtheory of this matrix as a block of this matrix. So I've deleted some rows, and now I have a subtheory. And so this subtheory is now just a matrix that has the same entries, but is now alpha L by alpha L, where alpha is between 0 and 1. And so this is my model for looking at theories embedded in larger theories, like these SUN is embedded in SUN plus 1. So alpha is discrete if L is finite, but it can be a continuous number as we're going to take the large L limit. And so what we want to compute is this ZL, Z alpha L correlator in this matrix model and see if it gives a similar result. And now alpha, we know how to interpolate. Okay. So in particular, I'm going to call this submatrix I'm going to take some deterministic projection P. And this is the submatrix PHP. So this is a rank alpha L projector. So we're in one matrix land now, and we can actually do computations. So I'll define the resolvents, or the trace of the resolvents, 1 over x minus h, and the resolvent for the compressed matrix, 1 over p y minus php. And we can compute this 2-point function, this connected 2-point function of resolvents for any such theory, or one-cut matrix model. All right. In lieu of time, I won't go through the derivation completely, but I'll give you just the ingredients. So we use just standard technology. We use the loop equation. With this resolvent inserted in the loop equation. So e to the minus L v of h. Okay, so the total derivative is 0. And you can get something for finite L, but we'll take the large L limit, because that's what we're most interested in, and things simplify. And what we find at large L is the following equation. And I'll define the pieces in a moment. Plus some polynomial. So this is the 2-point function that we're interested in. S is some single trace object. That's a bit complicated, but we can compute explicitly. This is php to the minus 2 times p. And then this is just fixed by the decay of w at large x and large y. It's some polynomial. The key input here is, so we have this somewhat complicated expression that mixes, it's a single trace, but it mixes lots of h's and p's, which aren't commuting. But at large L, p and h are freely independent, which is the statement, more or less just the statement that the eigenspaces of p and h are random with respect to each other. So p was some deterministic matrix that just projected you into this block, and h was drawn from an invariant ensemble, so these have completely scrambled eigenbases with respect to each other, and so people in math will call these freely independent. And a lot of technology has been developed for calculating complicated correlation functions of freely independent variables. And so I use these technologies to find that this has some simple form. G is the expectation value of R. Divided by L. So it's the difference in G and then this, where W is some function, some explicit function. Okay. So this works for any one matrix model. And then, so we use the loop equation and the free independence. And then we note that this equation that we found really just says that this W that we have at some value of alpha is some just transformation of the same 2-point function, but now without the alpha. So I'm just calling that alpha equals 1, x, but now I change y to w of y, and I take some derivative of wy. And this is a completely universal object. This is the 2-point function of resolvents. So this is universal for one-cut matrix models. It has a simple form, so let's assume that the cut, for simplicity, is between minus a and a. That's where its support is. Then this has a completely universal form that describes the ramp. So that's for any one-cut matrix model. It only depends on the endpoints. And so now, with this general formula, the input is the resolvent and this universal formula. And so we can just choose our favorite random matrix model now, and I'll, for simplicity, choose GUE, where this resolvent has a very simple form. And well-known form that describes the semicircle law. This is the semicircle. And from here, it's just plug and chug to get the microcanonical spectral form factor. And so I won't do the plug and chug. But you find that this y of t with this cross correlation, so the analog of the double cone with the D3 brane, you get t alpha to the t. And so this is t, okay, e to the minus delta s t, where I've defined delta s in this matrix model. It's the change in the entropy between the two theories. So in the matrix model, the entropy changes. The log of L is the entropy. And so the change in the entropy is log of 1 over alpha. So as you change the entropy more, it decorrelates more. And in say n equals 4, if you change n by 1, or if you just do a derivative, the change in the entropy was n times delta n. Because it's a matrix, if you take n to n plus 1, you get order n more degrees of freedom. Okay, so this is the same structure for these matrix models, this decorrelation where you get many different independent degrees of freedom between n and n plus 1 that we get from this double cone, from this gravity computation, which I find suggestive that we're on some sort of right track here. And this is where I've left it. Thank you.
So question for Jonah?
I mean, I barely even need the mic for this one. Just a tiny thing. What's the alpha subscript about on S on the right-hand side here?
On here, yeah, everything should have, everything depends on alpha. So I'm sorry for the bad notation. I've dropped some alphas. This should, W depends on alpha. Yeah. You can see because P is a rank alpha L projection, this explicitly depends on alpha.
So my main question is why do you think that averaging over n is enough? It's let's say some averaging is needed, but n, even when you create it continuously, it's a single continuous parameter. It's but the bulk physics presumably it has the semi-classical closed universe has larger space dimension. So why do you think that averaging over n is enough?
Well, I probably don't think it's enough. I don't know what else I could possibly be averaging over when you have fixed theories like in these higher dimensional versions of ADS CFT. It seems like that's my best bet right now, and so I'm just trying to explore what happens if you do it and whether it's enough. It seems, as I said before, there's these fluctuations that are, I get a 1 over, I can get convergence of the first term and the 1 over n term by averaging over n, which is better than not getting a limit at all, which is what happens if I don't do it. And averaging over t, I think, just doesn't make any sense because you don't have to, nobody's forcing you to do it. There's no ambiguity there. So it's out of desperation, and yeah.
One second.
Sorry, I just wanted to ask a basic point. So oftentimes in top-down ADS CFT, you can also oftentimes precisely determine what n is in the bulk, because if it's related to, for example, integer quantized flux. Yeah. So from that point of view, it's a bit mysterious why we have to do average over n, or why it's natural, even from the bulk point of view.
Yeah, I think if you're working on finite n, you shouldn't. I definitely don't want to say you should do this. I think, and if in ADS CFT at finite n, it's just some equality between the two theories. And then when we take the large n limit, or the semi-classical limit in the bulk, we get some answer from doing the gravitational path integral, but we're losing some aspects coming from losing some of this UV stuff, because we're just doing some low energy gravitational path integral. And so the question that I'm trying to look at is, what is the dual of getting rid of all of that stuff in the bulk? Because if for these things that don't have good limits on the boundary, they also don't have good limits in the bulk, because it's they're both sequences of numbers, and if one doesn't converge, the other won't converge. But we get some answer on one side, and I'm trying to interpret what that could be on the other side. I don't know if that's...
Well, I was just asking, even in the bulk, there is a logic which tells you that you need to quantize n, if it's related to the flux quantization. So that sounds like they're even within the logic, within the bulk, seems like one can specify n, but and then averaging over n seems like a very radical thing, even in bulk. So
yeah, I think it is. I don't. It's not a natural thing to do, but I think there's some ambiguity that can happen if you take the strict large n limit, and what we're really doing is some asymptotic expansion around n equals, or g nu n equals 0, or n equals infinity, and that's where we can treat n as a formal parameter as opposed to some strict integer. So that's the philosophy here. It's definitely, I don't want to mess with flux quantization. Yeah.
I have two related questions. The first one is, you don't consider, if you're saying that the states that you're computing, the averaging over is for every n, right? You're saying that your average theory is going to be separable in those operators, basically, that you won't have any n and n plus 1 operators, and you need to compute expectation values of those, and those will not contribute to that sum, to that averaging in some sense. In other words, I'm also asking, the second question is whether what this averaging over these operators actually means. You're not averaging over CFTs. This is not CFT data. Well, it is CFT data, but it's not of a single CFT, right? But at the same time, you also said you're not averaging CFT. So, what are you doing?
Yeah, the philosophy is just I don't have other parameters besides n, and I'm taking a large n limit.
I understand, but you don't have any, crossing symmetry between these operators. So, are you doing some sort of average over CFT data in the same sense? That
I think it's a bit different. For example, I think you could so crossing symmetry, you could get something adds to 0. You could get from the crossing equation, and I think you don't want to mess up anything like that. Like all of those are still going to be 0 when you do this average, because those things are they're 0 in every theory. So on average, they're 0. They have no fluctuations. So you definitely you have to be careful that you're not messing up things that you know are true already. Mm-hmm. I think there's some mysteries left over in the semi-classical limit of quantum gravity that can't be that haven't been explained yet, but we don't want to mess up the things that we know work. For example, like crossing symmetry.
Jonah?
I forgot my question already. It had something to do with.
Yeah. So, could you maybe explain again exactly what was going, let's say, wrong with the D3 brain example? Because I think when I came up with this question and then forgot it, it was supposed to be following up Shota's remark about flux quantization. I feel like if we're just doing the gravitational path integral, it's kind of fine to make n continuous for most questions. But then when you had the unbalanced spectral form factor and you added the D3 brains or Santos and Raghu and co, I mean, then they had to be integer quantized. So even if the bulk saddle didn't care whether n was an integer or not, if you consider this asymmetric Zn and Zn plus delta, then you need to add some discrete integer quantized things. And so that's the problem that I was bothered by when you brought it up. But then could you explain why their resolution of just adding the discrete quantized thing doesn't explain this phenomenon? Why doesn't it suppress the fluctuations? Why is this unsatisfying, basically?
Yeah, so from their calculation, you get this for the D3 brain, where delta n is a fixed integer.
Yeah, fixed integer, yeah.
So I'm interpreting this formula as I'm thinking about delta n. I want to think about delta n as now some continuous parameter that's not an integer.
Right.
This is just an interpretation. And from that interpretation, as I stretch apart in n, I have a correlation length of 1 over nt.
Mm-hmm.
That was something just observed from these calculations that were at fixed integer delta n. And then my motivation for looking at the random matrix is I know actually how to make delta n a continuous parameter in those theories. And so is this interpretation consistent with somewhere where I actually know I'm doing the right thing? So here I don't know that I'm doing the right thing.
Mm-hmm. Okay.
So here delta n should be discrete, yeah, for sure.
Yeah.
But if I want to explore continuous n, then I could have some interpretation for this formula. But I don't know how to do this in n equals 4 yet.
Okay.
Thank you for a great talk. So I have a small question about this comparison between the matrix model computation and the computation on the gravity side. So as far as I understand, you get a nice agreement with this extra e to the minus t factor, but how universal is it? So suppose instead of rescaling my matrix with the parameter alpha as you did, I add a small submatrix to my random matrix, which is totally uncorrelated. So in your case, it was totally correlated with the initial one because you single out a block.
Yes.
But what if this block is uncorrelated? Would you get the same answer or you get something different?
Yeah, good. And I should have mentioned this. There's work in the random matrix literature and in the gravity literature on, instead of changing n or changing the entropy of detuning couplings or adding in some uncorrelated matrix, which is like detuning couplings. And you get a very similar answer where this is related to the change in the couplings. So this has been done in, like, I think, like if you had just, if you look at plus or minus lambda times some other GUE matrix I'll call B. So, but there's some universal answers there for these kinds of detuning, and people have reproduced this kind of thing when you change couplings on the two sides in ADS-CFT.
But do you also get this exponential e to the minus t factor, or is it different?
No. You get in these detuning cases, but keeping the same value of n, you get t e to the minus, some function of this lambda times t. So you get something very similar. So changing n has the same form as changing a coupling.
Are there any other deformations you can add where the answer will not be of this form?
Are there other deformations where it won't be of this?
Well, because right now, when you change n, it seems that you can interpret it as either truncating your matrix by a factor of alpha or adding some extra perturbation which is uncorrelated. But are there any other deformations which don't produce the answer like that?
Oh, not changing a coupling and not changing.
Yeah.
I mean, if I'm not sure I understand.
Okay, maybe we can discuss later. Yeah, thanks.
Okay. Is this fixed by some sort of dimensional analysis? Is that what you're?
Yeah. This is my complaint that they always look the same.
Yeah. So in this Kudler-Jensen paper I mentioned, they were interested in these detuning, and they matched things between the universal stuff in random matrix theory from detuning and some double cone with some profile for the fields. And then my question is do you get something similar if you change the entropy? And you do. So maybe there's something. I don't know what another option would be to tune, but maybe this is just fixed.
Yeah, thanks for the great talk. I was just wondering, at some point you mentioned something about how you could put n-cubed independent samples, I think, at low times, and then it gets exponentially better at late times. Yeah, what is the interpretation of that? Is it just that at low times you actually cannot get more than the leading term in the perturbation theory, or do you think you can do better?
Yeah, it's okay. So this dip time. This dip time was order n, and so this is when I had. If I want to go to the scenario where I have the biggest problems, it's when I have the smallest times.
Yeah.
And so at this point I had n-cubed variables, and I don't know, and I still have a problem in perturbation theory, it seems. Although Juana just told me that there's no 1/n corrections for the spectral form factor, so maybe it's consistent, but to this t parameter. Okay, but then if there was, in other cases we do have a whole perturbative series, for example, the baby universe case, and then you'd have to go to, at these late times, then you have some exponential amount, and maybe it doesn't have to be all the way plateau. But,
yeah, okay. So the main point is that I need to wait until late times if I want the whole perturbative series, and I don't have no corrections.
Yeah, just you have to wait till longer than polynomial times, which on this graph is just right here.
Okay, great. Yeah, sure. Thanks.
But this is this means that the problem hasn't been solved over here. If it was exponential number of samples at all of these times, then I would have been much happier, and I would have claimed victory.